So section 1.6 in your book talks about probability. And previously we've talked about, using data that we have in order to predict outcomes and maybe model outcomes and make judgment calls and good decisions. And then I think probability sums that up in one word, which is, oh, is that really going to happen? Probably. Maybe. No, I mean, not likely. So all of those things really boil down to this probability. So does probability mean yeah for sure? Or does it mean not likely? Not likely? What's up? Okay, so we will talk about quantitative and qualitative measures for center a little bit. And we've used these before. We're going to do it again. Use frequency tables and relative frequency tables. We will compute probabilities and interpret them. And we're also going to try to make good judgment about when we're making inferences and when we're just describing what we know. So let's look at example 1. Okay, this refers back to that example where there were 24 Army inductees and their blood types. Notice here I don't care about gender, so I don't care in general. So here are 24 Army inductees, and but now we have some additional data. At Big Back Barbecue, they randomly selected to observe 10 of their patrons' waiting time before placing their order. Okay, so they're sitting there and they're like, are they patient? How long did they have to wait to get served? They recorded the wait times. Oh, there's a list of wait times. Got it. Okay. Which of these data sets is put into a frequency table? Oh, okay. I'm on it. Blood type. Thank you so much for organizing it. Done. Which set of data is qualitative and which is quantitative? Oh, so I have to remember qualitative is a quality. Quantitative is a numerical measure. Well, these are not really numerical measures. We're not measuring blood type. We're saying, what is your blood type? Oh, it's type A. That's a quality of blood. And then here, and we're just counting how many. Here, though, this is a numerical measurement for each one. So you have to think about the research question. Here, the research question would be, or the question asked to the Army inductee would be, what's your blood type? And then they would say, oh, you know what? I'm type O. And then that would be their response is type O, which is not a quantity. It's a type. It's a category or a quality. But here they would ask the patron, okay, how long did you have to wait to get served? And then you're like, oh, you know what? As a response, the person would say, I waited 4.5 minutes. And that is a numerical measure. So quantitative here, wait time. Wait time. That's a numerical measure, whereas blood type is a quality. So what's your blood type? Oh, I'm type AB. I actually don't know my blood type right now. I have it on some piece of paper somewhere. Anyway, it's kind of sad. And then this is a totally different type of question where you answer the response is in a numerical measure. For which set of data can we find the mean average? Okay, now I'm just expecting that many of you know how to compute the average. In order to compute an average, you have to add them all together and divide by how many. You cannot add up blood types. I mean, if you added these up and then you divided by 24, you should get 1, as in 100% of all of these people have some sort of blood type. But here, if we added up 5 plus 8 plus 20 plus 3 plus 4 plus 1 plus da 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 da, and then divided by these 10, Then we would find an average wait time. So for which set of data can we find the mean average wait time? But because they're quantities, we can add these up and divide by 10 to give us an average wait time. But we can't really find an average blood type. Okay. For which set of data can we create a relative frequency table? Oh, so now we have to remember what that is. Relative frequency was either a fraction or a fraction of the whole or a percentage. Okay, so just to remember what this is, fraction, portion of whole, or percent. Okay, well, we can't really do that for here. 5 out of what? What fraction? What percentage would 5 be out of here? But here, these are all out of 24. So we could create a relative frequency table for blood type. We could go 5 out of 24, 7 out of 24 are type B, 4 out of 24 were type AB, and 8 out of 24 were type O. So we could immediately make a relative frequency. Okay, which brings us to probability. Okay, for me, I define probability as a numerical description or measurement of how likely an event will happen or take place. So let's write that down. A numerical description or measure, if you will. Of how likely an event is to happen or actually take place. And in your book, they define a probability as a fraction. And it's true, it's computed as a fraction. It is the number we care about out of the total. So, number care about out of total. Total possible. For instance, up here, and notice that looks very much like a fraction, yes? For here, like, oh, you know what? What is the probability of somebody being type O? Oh, look, 8 out of 24, because there were 24 of them and we had 8 of them. 8 out of 24, that's the ones you said you cared about, and there were 24 total inductees. So 8 out of 24, that's a probability. Okay. And so now we're renaming something that we already named. We said that was the relative frequency. It is. It gives the frequency relative to how many were actually inducted. But it also is giving us the probability. What are the chances of one of these Army inductees being type O? Oh, well, 8 out of 24 is your chance. Okay? Okay, so a few remarks. So we're almost treating them like synonyms. Probability can be written as a ratio portion. So okay. Ratio, fraction. Okay. Also, probability could be written as a percentage. Because once you do 8 divided by 24, you can actually turn that into a percentage. Yeah. Okay. Or decimal. I mean, to me, when I think about percentages and decimals, they're just so linked that I just don't separate the two. But anyway, let's write them both down. We've used fractions and percentages in qualitative situations before. So, like I said, this, I mean, if you, we already talked about that example and did this to it. So, just want to refresh your memory that, but now I'm tagging it with this qualitative so that we can start keeping track. So, qualitative situations use fractions and percentages. Okay. But in quantitative situations, we use the mean average. So the average wait time. So quantitative data allows us to compute averages. But this qualitative data, it counts on the probability or the percentage. So while qualitative uses probability. Okay, so just kind of a different measurement to get at a description in order to make good decisions with two different data sets. Okay, 0% probability means it is not going to happen. So 0% probability means it is not at all likely. I usually, in my mind, tack on to happen. 100% probability means it is surely going to happen. Oops. I like to alternate colors because it helps me read. Yep, forgot. All right, let's take a peek at example 2. We light up your life. The company We Light Up Your Life wants to know how many of their light bulbs are defective. They randomly test 80 of their light bulbs in a 24 period of production. Got it. 24 hour, whatever. A day. Was a sample taken or was the entire population included in this test? Well, it says that they tested 80 of their light bulbs. I'm guessing that they don't just make 80 light bulbs per day. So, sample. Yeah? Not every light bulb was tested. All right, let's write that down. That was definitely a sample. Do we know the sample size or the population size? Well, we know the sample size. They sampled 80 of their light bulbs and tested those. So the sample size is 80. How many light bulbs they made in 24 hours? Not sure. Doesn't say. If 6 of the tested bulbs were found to be defective, what is the probability of getting a defective light bulb? Well, that would be 6 out of 80. So 6 out of 80. And now I'm going to get my handy dandy calculator. I'm going to go 6 divided by 80 and times 100 to turn it into a percentage. And I got precisely 7.5%. Uh-oh, write it as a ratio and as a percentage. Okay, done. But I need to fix this because ratios have labels. And not only am I going to fix it and include a label, but also maybe I'm going to simplify that. What's 80 divided by 6? Ugh, gross. This simplifies to, well, they're both scalable down by 2. That would be 3 out of 40. Okay. There are 3 defectives for each 40 bulbs. Okay, out of 40 bulbs, 3 defectives. So here it is as a ratio and 7.5% defective. Let's write that down. Okay. If 6 of the tested bulbs were found to be defective, what is the probability of getting a bulb that works? Oh, well, if 6 of them were bad, then the rest of them were good. What is that, 74? So I'm looking at this and I'm thinking, well, that is 74 out of 80. Or, you know what, 100% of the bulbs were tested, well, 100% of the 80 bulbs were tested. I bet we could do 100%, take away the 7.5 that happened, and get 92.5%. So 74 divided by 80, 92.4%. Write it as a ratio and as a percentage. Defective. What is half of 74? 37. 37. Oops. Good bulbs for each 40 bulbs. Got it. There it is as a ratio, and here, oopsie, I labeled it as defective. Boop. Good ones. Keepers. That's a keeper. All right. So, a few words that we've been using, and I'd like to write them down. First, the population is the entire group being studied. And the sample is just a subset or a subgroup of the group being studied. So here, 80 of them, 80 out of all of them. And the population is all of the light bulbs in a 24-hour period. Individual is one single person or object that is a member of what is being studied. A single person or object is a member of the group being studied. Okay, and I'm going to give us a few remarks before we do example 3, where we and finish it out, where we compute a bunch of probabilities. First, error can occur due to taking a sample instead of using the entire population, of course. So okay, when making decisions, okay, because you really didn't ask everyone in the whole group or study every light bulb. We really just studied a few and then, you know, made a pretty good guess about the rest. But that guess could be a little bit off, like a hasty generalization kind of. And then, a biased sample is one that does not represent the population. So, A biased sample does not represent the population. For instance, if I were going to ask a class if I have no idea what I would ask an entire class. Well, the most frequent thing that I ask is, hey, did you have a good weekend? What'd you do this summer? Whatever. But if I only asked maybe people 19 and under what they did that was fun during the summer, then I definitely would not be representing the whole population of my students, because I have a ton of students who are older than that. The majority of my students are older than that. So that would definitely be a sample that does not represent the whole population. And people do this, I mean, sometimes they do it by mistake. Most of the time they do it by mistake, I would say. Like, it's just a convenient thing. So maybe you took a poll of people, of students, and you only went to the cafeteria, not realizing that a whole sector of our student population never goes to the cafeteria. I mean, they might go to Job Lounge, but not the cafeteria per se. So just saying, like, sometimes this happens without being on purpose. But still, the data gets thrown away if that happens. And then data entry itself, the human aspect can cause error in a research project. So just so that everyone knows, research isn't perfect, and we try to do our very, very best to control all of these things when we are doing it. So data entry can cause error too. We have to be careful. Okay, so I say all of these things because when we're studying probabilities, more often than not, we are collecting data, and we need to be very careful about, like something as simple as accidentally recording these. Like, maybe that was supposed to be a 2. Did someone really wait for 20 minutes before getting served? If I had to wait for that long, either A, I had a bottle of wine there, or B, I kind of looked at him and I was like, maybe I should just go. So, I mean, I look at that and I'm like, maybe it was really supposed to be 2. Did the person recording the data do it right? Is that right? Anyway, so that can happen, okay? In the next video, I'm going to go through computing probabilities, and we'll work on making some decisions from each one of those.